In this video, I'm going to walk you through the process of solving a vector equation. So let's take a look at what we have. These are the pieces you might be given, okay? So this is a common exercise in calculus books. You may be given the following pieces of information. You may be given a vector v, so I will color code a vector v, and the components of this vector might be 2, 1, and you may be told the following fact, that this vector here is a linear combination of two other vectors. Okay? So it's a linear combination of two other vectors. And it's given the following way. There's a constant a that multiplies one of these vectors, okay, such as the vector u. And then there's another constant b that multiplies another vector, and let's say we call that vector w. So let me not reuse these colors here. Okay? So this vector v is a linear combination of two other vectors. One vector is u and the other one is w. And the constants multiplying these vectors are a and b. And the question is, after some mathematical magic, can you find a and b? Can you find those constants? Given all of these pieces of information. So let's take a look. Let's write down the fundamental fact, which is that the vector whose components are 2 and 1, which is v, equals a times vector u. But vector u, say, has the following components: 1 and 2. And 2, we are adding a multiple of vector w, and the components of vector w are 1 and negative 1. Okay, so 1 and negative 1. There we are, okay? So the vector 2, 1 is a linear combination of the vectors 1, 2, and 1 and negative 1. And the exercise says find a and b, these two scalars. Okay? Some people call these weights. So how do we find them? Well, let's take a look at what we have. If you look at this, you see that you have two unknowns, so you probably should end up with a system of some kind. First, let's simplify the right side a little. Okay, so on the left side, we still have our 2, 1. But on the left side, on the right side now, what we will have is this. We multiply the a into each of the vectors, okay? So I will use the following. Okay, the rest of it, for the sake of consistency, I will write with one color, okay? So we have a, and then we have 2a, plus b, and then we have negative b. So all I've done is I've distributed the a over to the components of the blue and the b over to the components of the purple. So now what we have is this setup. So once again, this red vector 2, 1 will be equal to, now you combine the x components from these two, a plus b, and then 2a minus b as the y component. There we are. So these are the components of our vector. And the only way the right side can equal the left side is if a plus b equals 2 and 2a minus b equals 1. So let's write that as the next. In other words, now we are transitioning into a system of two equations. A plus b equals 2, and then 2a minus b equals 1. So we began with a vector statement, a vector equation, but ultimately to solve for these constants a and b, you've got to transition into just a system of two equations and a and b as the variables. All right, so how do we solve this? Well, we can use the method of addition. Take a look. If I add these two equations together, you see that the b's, of course, will cancel. Excuse me. So let's do that. So add straight down, then a and 2a is 3a. A b plus a negative b is 0. 2 plus 1 is 3. And take a look. To isolate a, divide everything by 3. Therefore, a equals 1. Okay. A is 1, okay? So we are super close. And then take a look at the next step. If a is 1 and a plus b is 2, then b must also be equal to 1, right? Because 1 plus 1 is 2. So b equals 1 also. So this approach is purely algebraic, and it reveals that the scalar multiples acting on vector u and then w are simply 1 and 1, which means the following, that the vector v, okay, can be expressed as the following. It's 1 times u, okay, so it's one of the u's plus 1 w, like this. Okay, that's what it's telling us. The vector v is 1u plus 1w. Okay, let's check this to be sure this actually works. Well, what is 1u? U is just, we are told, is 1 comma 2. So you write here 1 comma 2, and then you add to it 1w, so that's just a w unchanged, which means that means you write 1 comma negative 1 like this, okay? And now you operate on these. So 1 and 1 is 2, correct, checks. 2 plus negative 1, of course, is 1. There you go. So this shows that the vector v really is a linear combination of u and w, and the constants a and b are 1 each. This is your a, this is your b, and this confirms that v is a linear combination of u and w. Okay? So remember, you're beginning with a vector v, then you're told it's a linear combination of this form of the other vectors u and w. So you're right, 2 comma 1 has to be equal to a times 1 comma 2 plus b 1 negative 1. You distribute the a's, distribute the b's, as I've done here. Then you combine, so the a plus the b is a plus b, 2a plus negative b is 2a minus b at this step. Then you transition from a vector equation to a scalar equation. So you've got a plus b equaling 2, and the other condition is that 2a minus b must be equal to 1. Then you make the observation that the b and the negative b are set up to cancel, so you add the equations together, and you end up with 3 a's. The b's go, and then 2 plus 1 is 3. To isolate a, divide both sides by 3, and you find that a equals 1. Now, for a plus b to be equal to the number 2, if a is 1, then b must also be 1. So b is 1. And now this last sequence of manipulations is simply a check to confirm that these are the correct values of a and b. So 1u means 1 comma 2, 1w means 1 negative 1. 1 and 1 is 2, 2 plus negative 1 is positive 1, and it checks. In other words, this vector is the same as the given one here. There you go. Thank you for watching.